Okay, hello everybody. My name is Brent Everett. I'm a pure mathematician in the mathematics department at the University of York. So welcome, and it's my great pleasure to introduce Rob Ainsley, who's today's speaker. So Rob describes himself this way, and I'm taking this from his webpage. He was once briefly the top-rated mathematician in the UK in his age group. Unfortunately, that age group was 17 years and 215 days. I know how he feels. He did a maths degree at Oxford and trained to be a teacher, but making a significant positive contribution to mathematics education by actually not becoming one. So Rob is a writer and an author, mostly about cycling. He lives in York, but is usually away on his bike somewhere unpronounceable. Maybe he might tell us where he's going somewhere so we can hear one of these unpronounceable names. So he's the author of 2 books on mathematics, How to Bluff Your Way in Maths and How to Sound Clever at Maths. So Rob, welcome, and over to you.
Hi, hello everyone. The things I'll be talking about today came from this book, How to Sound Clever in Maths. The story was it was commissioned a couple of years ago. I wrote it, and the company which commissioned it then, for whatever reasons, canned a lot of their titles, a lot of divisions shut down. Perhaps it was due to the pandemic, but correlation is not causation, as we know. Anyway, we'd organised some talks, and this is one of them. So we're going ahead with the talk, and I hope you enjoy it. And if you want to have a look at the book, you can actually find it. It's on my website, and you can download it for free. And the story was I did a maths degree and sort of fell out of love with maths a bit. And I think I was a bit in denial. I didn't like admitting that I was a mathematician, and I was sort of a bit embarrassed to hang around with mathematicians. And later on, particularly in the YouTube era, I started looking at videos on popular maths and really got back into it with a sort of renewed enthusiasm. And it's a bit like meeting up with an old flame, an old boyfriend or girlfriend, and you think, well, why did we ever part? This is great. We're made for each other. So I definitely now feel sort of quite pleased and proud to admit to being a mathematician. And I think some of that feeling, I hope, comes across in the book. It's a bit of a love letter to maths and a very affectionate kind of look at maths and mathematicians. And I'll try and get some of that across today. This is my website. If you find that page, you'll be able to download a PDF of the book. That's the sort of rough cover, and the significance of the orange will become apparent. I'll be talking about some fun sort of tricks, almost like magic tricks that will get people really intrigued. And I've test driven a lot of these things with people, and I'll be covering some of the things today that I know really work from experience and actually get people really engaged. We'll be looking at this strange method of multiplication a little bit later. We'll also be finding what this bridge in Hull has to do with Venn diagrams. And we'll be looking at the world's largest hotel, which is this. It's the White Lion in Machynlleth. And we'll be looking at those oranges, how to take one orange, chop it up into pieces, rearrange the pieces into 2 oranges, each the same size as the original. We'll be looking at what actually happened when they gave some monkeys a bunch of typewriters. And we'll be talking a bit about infinity, and the theme of the Festival of Ideas is infinity. And infinity, of course, is such a basic principle in maths that it's everywhere. And one of the most curious aspects of infinity that always blows my mind is that some infinities are bigger than others. So the infinity of all the whole numbers is actually smaller than the infinity of all the numbers you can write down. And one of my favorite examples of how infinity can really mess with your intuition is this thing, the Banach-Tarski paradox, named after 2 mathematicians, sort of late 1800s, early 1900s mathematicians. And this is where the oranges come in. And sort of to explain what's happening, imagine you take an anagram of the phrase Banach-Tarski paradox. So you put it in an anagram generator online, And you get various possibilities. And one of my favorites is toxic Arab panda shark. Now, a panda shark is actually a thing. If you go into Japanese manga, you'll find there is in various fan sites something called a panda shark. But the interesting thing happens when you put the phrase toxic Arab panda shark back into the anagram generator, because it's like what you get out is 2 copies of the original. You actually get Banach-Tarski, Banach-Tarski, paradox, paradox. You get twice the volume of letters that you had in the first place. You get 2 complete copies of the original. So the idea is the Banach-Tarski paradox, it's a recipe for chopping up a sphere in a finite number of pieces, and you can then rearrange these pieces to get 2 spheres of the same size. How does it work? Well, it's all a bit complicated. If you're interested, there's an account in a book by Ian Stewart, a popular mathematics writer, and it's readily understandable by any algebraic topologist postdoc. This is effectively what you're doing, chopping one orange into pieces, but the trick is that the pieces are infinitely wiggly. And that's when it starts to mess with your intuition, because our intuition about volume and what volume means sort of breaks down here. And so that's where the paradox comes in, that it feels wrong to have twice the volume you started with, but that's kind of what happens. And perhaps an easier way to get a feeling of the kind of strange things that happen with infinity and how our intuitions don't work is the concept of a full hotel. Now, we know what it means to say a hotel is full if it's a finite size. This is supposedly the largest hotel in the world. It's the first world hotel in the Genting Highlands in Malaysia, and it's got 7,351 rooms. We know what it means if that's full. It means there aren't any more rooms, and if you turn up and try and get a room, you'll be out of luck. But what if the hotel has an infinite number of rooms and it's full? Is it really full? And this is where things start to get a bit more interesting. This is actually the world's biggest hotel, and it's the White Lion pub in Machynlleth in Wales. And I know it's the biggest hotel because I stayed there in 2013 on a bike ride, and that was my room key, and it's got an infinite number of rooms. So is it full? Well, this guy's David Hilbert, or David Hilbert, Herr Professor Dr. David Hilbert from the Universität von Göttingen, turn of the century mathematician, a very significant figure. And he came up with this idea of a Hilbert hotel to explain some of the strange things that happen. The idea is you've got this hotel, infinite number of rooms, and it's full. Somebody turns up and asks the receptionist, "Can I have a room?" And the receptionist says, "I'm sorry, we're full." Hilbert sort of appears, taps him on the back and says, "Actually, no, we're not full, we can find space." And here is how we do it. We move the person from room 1 into room 2 into room 3, 3 into room 4, and so on. Everybody has a room, but we've freed up room 1. So we weren't full after all. In comes the person. Great, sorted. Then 1,000 people turn up, and the receptionist thinks, I know how this is going to work. I'll move the person from room 1 into room 1,001, 2 to 1,002, 3 to 1,003, and so on. We've freed up 1,000 rooms. There we go. We weren't full after all. Well, then a coach turns up with an infinite number of people in it. And the receptionist says, "Oh no, we're beaten here. We really are full. I can't fit in an infinite number of people." And Hilbert says, "Yes, we can. This is what we do. We move the person from room 1 to room 2, 2 to room 4, 3 to room 6, and so on. Everybody moves to the room that's twice their number. So that way we've freed up all the odd numbers, and there's an infinite number of them, so all the people can have a room. So we weren't full after all." Well, actually, you can extend this. So even if an infinite number of coaches turn up, each with an infinite number of people, you can still find space. And even if you have an infinite number of ferries turning up at the same time, each with an infinite number of coaches, each with an infinite number of people, you can find space for them. So it's one of these strange illustrations that what does full mean? When you've got infinite stuff, strange things happen. And here's another slightly mind-bending thing about the nature of infinity. The expansion of pi, people know what pi is, it's the ratio of the diameter to the circumference of a circle, crops up all over the place in maths, and you can never write it all down because it goes on forever, never repeats. There's an episode of Star Trek where Spock very cleverly confounds the computer by telling the computer to find the last digit of pi. Well, of course, there's no such thing, it goes on forever. And it never repeats. And there's some technical aspects to this, but broadly speaking, you can find any sequence somewhere in pi, however long. At least you can say the probability is the longer you look, the higher the probability you'll find it. So any sequence is there. And that means if you encoded the complete works of Shakespeare with A is 0, 1, B is 0, 2, and so on, wrote it down as a huge long number, that'll be somewhere in the expansion of pi, the complete works of Shakespeare. In fact, every book ever written will be in there somewhere. The 1959 Haynes Workshop Manual for a Ford Pop, it's in there somewhere. Your teenage diaries, they're in there somewhere. It's a scary thought. And that brings us to the monkeys. Now, obviously, this is a chimp. It's not a monkey. It's from an album cover, 1979, by the Mekons. It was rubbish. Don't bother looking for it. But they actually did try to see what happens when you give a load of monkeys typewriters. Now, it's a sort of trope to say, oh, you give an infinite number of monkeys typewriters and they'll produce the works of Shakespeare. It's featured in many comedy routines and books. It's mentioned in one of the Hitchhiker's Guide to the Galaxy books. And it's a bit of fun, basically. But in 2003, I think the University of Plymouth actually gave 6 Sulawesi macaques typewriters to see what they would come up with. Here's 2 of the macaques, 2 of the authors. It's now a book. They've actually produced a book of what they wrote. It's in the British Library. You can find it. And here is a page of what the monkeys came up with. It largely consisted of the letter S, and they spent a lot of time defecating on the typewriters. It's not really very Shakespearean. I don't think there's any iambic pentameter there. So it's a kind of reminder of just how far away we are from infinity. They didn't even get as far as to be or not to be. You know, there was nothing really interesting in there. But here's a couple of things you can kind of try with friends, and these are guaranteed to get them engaged and guaranteed to get them often quite puzzled, and they'll think you've pulled some sort of magic trick on them, but it isn't. It's just pretty straightforward maths. And the first is a way of multiplying without multiplying, sometimes called the Russian peasant algorithm. It's actually nothing to do with that. Apparently the Egyptians used it, many cultures have used it, and it's a way of decomposing a multiplication in a strange way, and the first time you see it, it really isn't obvious what's going on. And here's how it works. We're multiplying any 2 numbers, works for any 2 numbers, but we'll just take 37 and 19. 37 and 19, obviously you could do it on your phone, but there's no fun in that. What we're going to do is do it the Russian peasant algorithm way, even though the Russians never did that. And the way it works is you write one number and then the other number at the head of 2 columns. For the first number, you just keep halving it and ignoring any remainder. And then in the second column, you keep doubling the number. So 37, half of that is 18 and a half, ignore the half. Double 19 is 38. Half of 18 is 9, double 38, 76. Half of 9 is 4 and a half, ignore the half. Double 76, 152, and so on. And then, and this is where you can bring a bit of the theatrics into it, you tell them that the ancients, talk about it as if it's some ancient thing. Oh, the ancients knew about this. This is how Stone Age man would do multiplication. They believed that even numbers were evil. And so you have to strike out all the even numbers in the left-hand column and the ones that go with it. And then you add up the numbers that are left in the right-hand column. So you get 19, 76, 608, add them up, 703, and sure enough, that is 37 by 19. Now, I guarantee when you do this with people first time, they really won't know what's happened, and they'll fiddle about with all sorts of numbers and try and work out how it works. The thing to do is not try and explain how it works. You're basically just splitting the numbers into their binary parts. But the best thing to do, I think, is sort of sit back and just look smug, as if you can see something that they can't, and say things like, oh, children can see this straight away, but as adults, we just lose the ability as we get older. And that'll just get them a bit worried. Prussian peasant algorithm, always a winner. Here's another winner, Simpson's paradox. Sometimes stats can work in a way that surprises you. And best way to do it is just explain it. You are the manager of a company, and you've been told that you have to get rid of one of two employees. You just can't afford them both. One will have to go. And the way you're going to decide it is that the sales staff with the worst percentage record of sales is going to be out on their ear. That's the rules. You've got two sales staff. There's Alex and there's Bailey. Notice that I use gender neutral names there. And you've got two areas. There's the north and the south. Now the figures from the north have just come in. And here you can see Alex, 500 clients, 80 sales, success rate 16%. Bailey, 300 clients, 51 sales, success rate 17%. Well, the conclusion so far is Bailey's going to stay, Alex is going to go. Not much in it, but Alex has the worst record, and that's the rules. Let's see what happens when we get the south of England. Here's the figures from the south. Alex, 100, 10 sales, 10%. Bailey, 500 clients, 60 sales, 12%, and a lot more sales, actually. Well, it's clear, isn't it? Bailey's got a better record than Alex, both in the north and in the south. So no question, Alex is going to be sacked. They're the one that you invite into your office and explain that you're going to have to let them go, which is what you do. And then Alex's lawyer is on the phone, furious. And they say, how dare you sack my client when they have the better success rate? And you say, what do you mean? And say, well, look what happens if you add up the figures, the overall sales figures for Britain, not just north and south, not splitting them, but overall. That's what happens when you add them up. Alex has the better success rate. So what do? Well, of course, he can't do anything because it just happened, and it happens something like, I think, 5% of the time at random, that when you do this sort of thing, the trends can reverse depending on how you split them up. It's called Simpson's paradox, various other names for it. And a way to kind of visualize it is on Wikipedia. Wikipedia is your friend. Often, if you look stuff up on Wikipedia, there's really good things there. And this kind of illustrates what's going on. If you look at these 5 groups of dots, each of the 5 groups looks as though it's going uphill, left to right. But you put the 5 groups of dots together and they're clearly going downhill from left to right. And just those figures are sort of useful to jot down and take people through this scenario. And the reaction is great because people are convinced there must be some sort of trick to the figures. You've not added them up properly or something. But that's what happens. And it's an illustration that stats is only a tool. And if you're not quite sure what you're doing, you can end up trying to hammer a screw in with a hammer. And this does apparently has caused problems in real life. There was a famous case in 1973, University of California at Berkeley. had a lawsuit alleging discrimination against female applicants. And when you looked at the entire overall application figures, sure enough, there was a clear discrimination against women. But when you broke it down by department, there was a clear discrimination against men almost all the time. So stats can work in very mysterious ways. Yeah, that bridge. This is another thing you can sort of amuse people with. This is Drypool Bridge in Hull, and it celebrates one of Hull's famous sons, who's John Venn, the mathematician John Venn, who invented the Venn diagram. And this bridge celebrates the Venn diagram. They're supposed to be Venn diagrams. It actually looks like sort of 1960s shower curtain patterns to me, but what the hell? It's a bridge. It celebrates John Venn. There's John from Hull, so he must have spoken with a Hull accent, I'm sure. And he came up with the idea, he did a lot of work on set theory, and one of his lasting contributions has been the Venn diagram. Simple way of just illustrating things very clearly. If things belong to one set or another set or both sets or none of the sets. And 2 is obviously the simplest sort of illustration of that. If you've got 3, you can clearly cater for all possibilities. What about 4 though? If you try and do it with 4 circles, it's not immediately obvious perhaps, but you don't actually cater for every possibility. And, you know, again, it's the sort of thing you can try with people. There are 2 which are missing. There should be 16 possibilities altogether, and there's 2 that this doesn't quite cover, which is those 2, A, C, and B, D. You can't put on there something which is in it, a member of A, a member of C, but not the other 2. Ditto with B, D. You can represent 4 sets in this Venn diagram way, but you have to be a bit cleverer. And you have to use sausages or sort of kidney shapes or something. So here's an example of 4 Venn diagrams where you can cater for every possibility. And yes, that's just one I put together. You'll see that the only combination, which is a chemical element, an internet domain, a 2-letter Scrabble word, which you're allowed to use, and a Chinese president, is Li. It's possible to do it with 5. This is from the American comic strip XKCD. And you can, in fact, do it with any number, but the more numbers you get, the more convoluted all these shapes get. And you get incredibly sort of wiggly things that go in and out of each other. But in principle, it is possible to do a Venn diagram for any number of groups on a flat sheet of paper. So yeah, this is sort of the last amazing thing you can do to amaze people. It helps if you've got some dominoes handy or something like that, or possibly some identically shaped slabs of concrete. And this is the question of when you're stacking blocks up like this, it's fun to think how far can we make it lean over before it falls down? What's the furthest that one at the top could overhang the one at the bottom? And there's quite a surprising answer to this. You can see that to make the one at the top lean further over, you've got to have some more at the bottom. And in practice, it's quite difficult. I could hardly get one overhang, even with however many tiles it is, 12. If you're looking at it theoretically, and again, there's stuff on Wikipedia that tells you how to do it. Well, you can see that if you've got 2 blocks, you can have an overhang of a half. If there's just those 2 blocks on top, an overhang of a half before it'll topple over. If you have 3 blocks, well, it's a bit of sort of simple physics, but you can see that you can overhang of a half, and the overhang between the 2nd block down and the 3rd block down is 1 over 2 times 2. And each time you add a block on the bottom, the overhang you can have gets smaller each time. That's what it works out at 1 over 2 times 3, then 1 over 2 times 4, 1 over 2 times 5, and so on. You add all those things up, and you'll get that. But it can go on potentially forever, depending on how many dominoes you've got. So what does that add up to then? What's the biggest that'll ever be? Well, it turns out it's sort of the same as the biggest that will ever be. That obvious little sequence there. How big does that get? And the surprising answer is it can be as big as you like. You can make it 1,000 or 1,000,000 or you have to go an incredibly, unimaginably long way. You've got to have an unconscionable number of tiny fractions to add up. But in principle, it can be as big as you like. And so I think if you want an overhang of 2 blocks, it's something like 31 tiles that you need, or 31 blocks altogether, which is just a bit more than in a standard set of dominoes. That's 28. If you want 100 blocks overhang, well, you can do that, but you're going to need like more blocks than there are atoms in the universe. But that's the mind-bending thing. That tower that you were doing, which obviously, as it curves down, is going to get nearer and nearer and nearer straight. But you can make it lean over at the top as far as you like. And it's things like that that I just love about maths, and rediscovering all these things has been an absolute delight for me. There's loads of other stuff in the book, little things like spotting amusing shapes in everyday life, such as cooling towers, which are usually hyperboloids. And the reason they're hyperboloids is they're made up of straight girders. There's no curved girders in those, which is, again, it's a sort of not really an intuitive thing. You think they'd be rounded girders, but they're not. They're all dead straight. And it's, if you imagine you get 2 rings joined by straight girders and then twist one of them, you get that sort of shape. And other shapes, Humber Bridge, which is dear to me because I grew up here, exactly here in Ferriby, watching the Humber Bridge being built. And it started off as a catenary because there was nothing hung from it, but then they hang things on and it becomes a parabola. That is a catenary. That's a washing line, and that's my washing line in my back garden. If you've enjoyed this, well, if you visit this URL, you can get to my website, you can download the book, and I hope it'll give you some of the enjoyment and some of the enthusiasm that I've rediscovered, and some of the amazing, mind-boggling things that you find in the world of popular maths. There's also loads of stuff on YouTube and plenty of books, and I hope you've enjoyed that, and thanks very much.
Thank you, Rob, for that very amusing and very affectionate tour of some mathematics. Yeah, you said at the beginning something which really resonated with me. Actually, there's many things that resonated with me, but at the beginning you said that there was a time when you didn't really like hanging out with mathematicians, and in a way you're almost ashamed to call yourself a mathematician. And I definitely know that experience well. Back in the early 90s, if I went to a party, I would actually introduce myself as an undertaker rather than a mathematician, because I felt that it was actually, was probably going to have a more positive response. But I've noticed in the last 25 years or so that mathematics has changed. The perception of mathematics has changed, and mathematicians have become, first of all, more diverse, and dare I say it, slightly cooler. Do you have any insights into why this change has happened?
I agree. I think it certainly has. And I think there's 3 reasons. First, I would like to think anyway, that society has just become a bit more able to embrace and celebrate diversity. And we recognize that people different from us, with different talents and different likes and dislikes from us, all help to contribute to society. So, society's got a bit kinder, I hope. There's also just a general rise in popular media, popular culture. And you can see this with music or philosophy or science or all sorts of things. You can go on YouTube, you can find some fantastic videos which will explain how the Dorian mode works, or what Spinoza's theory of substance is, or how Fourier transforms work. All this stuff that was never available when I started doing maths in the 70s. And some of it is just so inspiring, and I feel a little bit envious of people doing maths now, because if you want to find out how to visualize these things, there will be something up there to help you. So that's the second thing. But the third thing I think is specific to maths, and that's that society has become much more technological. It's much more based on technology, particularly data. Data drives a lot of stuff now, and algorithms. You never heard anybody using the word algorithm outside of a university 30 years ago, and now everybody is aware that these things control aspects of our lives. You know, how Facebook decides which fake news to show you in your echo chamber, that sort of thing. But also the way that we know GPS is clearly very technical. It clearly has some kind of mathematical basis there somewhere. And I think there's a lot more recognition that, yeah, maths is now, whether we like it or not, we need mathematicians to operate all these technological functions. And so, yeah, I think we've become cool for a combination of those reasons. And now, yeah, very definitely, I'm very happy to embrace my nerdy side.
Yes, it's a very good point what you make about the internet. I mean, we have this generation now that have grown up entirely in the age of the internet, and they don't know anything else. And that has been, I think, a remarkable tool for helping people to find each other, to find other kinds of people like themselves. Before you were isolated in your room with your mathematics, but now you can find mathematicians everywhere. And
yeah,
yes.
I had an interesting story last night talking to a friend who I was at university with. His son is now an algebraic topologist doing a PhD, and his son has
we'll forgive him. We'll forgive him.
There's a lot of jokes about algebraic topologists.
Well, funnily enough, I am an algebraic topologist, so that's.
I have no problem with algebraic topologists, not in any way, shape, or form. But his son has literally just found out yesterday that the paper he was about to publish has been anticipated by this other bunch of Russian mathematicians. And so they're now trying to work out what should they do. Should they get in contact and collaborate, or should they try and beat them to it? And so, yeah, it's interesting, these kind of problems, although I suppose you get those problems in science generally.
Yes, I'm familiar with that problem. So another aspect of mathematics, which sort of I was struck by when I was reading your book, was that there's this sort of great irony I find with the subject. So on the one hand, there's a perception amongst the general public maybe that it's some kind of universal language. You know, if we're contacted by aliens, then we would attempt to speak mathematics to them rather than English. But on the other hand, I know from my own personal experience that mathematics is such a sort of an esoteric and abstract and sort of rarefied subject that if you get two mathematicians in a room together, they're incapable of communicating even with each other. They can't explain. I can't explain my algebraic topology to a number theorist and vice versa. So what kind of challenges, as someone who's trying to bring across the subject to non-mathematicians, what we like to call normal people, what kind of challenges do you find in trying to bring across such a subject?
I think the key is not to be too weighed down by the detail of our own speciality. And maybe there's a lesson to be learned from some musicians here. And it struck me that classical musicians now are much more versatile, I think, than they were 30, 40 years ago. And it's not uncommon to find someone who plays a lot of avant-garde modernist stuff by Brian Ferneyhough, but can also do rhythm and blues down the pub of an evening, and also play jazz over a weekend, and also do Piazzolla tangos. And so I think the way forward is that perhaps as mathematicians we can recognize that there's our speciality over there, and only about 12 people in the world will ever know what we're on about. But there's so much other stuff, so much of it. Sometimes it's popular stuff, and sometimes it may feel a bit hackneyed when you're seeing the polar bear problem for the 1000th time. But I think we have to be aware of this, and to be able to treat it each time as if this is the first time we've looked at this problem of the man shooting the polar bear, and is it the North or the South Pole, to engage people, and sometimes not just members of the public, but also maybe even other mathematicians. So I think it's taking a cue from people like musicians who are often quite happy to embrace all sorts of music, from the abstruse to the popular.
I see you have a guitar in the background there. There's often a strong connection between mathematics and music. A lot of mathematicians I know who are musicians. So you're a musician as well as a cyclist?
Yes, I also did a music degree and did some singing, and classical guitar is my instrument, and I write for that.
So just to, the one part of your book where I really did laugh out loud, I mean, people do use this phrase laugh out loud quite generically, but I literally did laugh out loud when you were describing the social skills, we say, of your average mathematician. A standard joke that I know is, you can tell an extrovert mathematician because they stare at your shoes rather than their own shoes. Your way of putting it was, during pandemics, mathematicians look forward to 2-meter social distancing rules being relaxed so that they can revert to their normal 5 meters. Yes.
Yes.
So I guess a slightly topical question now. I mean, COVID-19 is one of the great challenges that the world is facing at the moment, and is there a role for mathematics in helping the world there, and what is it?
Well, absolutely. And I think, again, there's this opportunity that we have, because for the first time I can remember over the last year, people are talking about exponential growth in a vaguely accurate way. And suddenly we're used to referring in normal everyday discourse to our rates, exponential growth, looking at 7-day rolling averages, looking at graphs, talking about trends in a way that I don't think we did before, because now we realize this data absolutely matters. And so what I would hope is that people realize that, all this maths thing actually has a very sharp and immediate relevance to us in our everyday life. So I would hope that we can come out of this with more respect for the science, more respect for the maths, and that we recognize that just because somebody stands up in front of us and talks in a very confident way and rabble-rouses a bit and talks in a populist manner and claims to have all the answers, well, for once, we've come up against something that even they can't talk down, even they can't bully, but the maths, the science, remains reliable. There are different interpretations, but I hope one of the lessons is that we can actually trust the maths.
All right. Rob. I'm glad that you're not ashamed anymore to call yourself a mathematician, and that you're happy to hang out, at least briefly, with other mathematicians like myself. I really did. I enjoyed your book, and I really enjoyed your talk. And as I say, it was a very affectionate view of the subject, which is obviously nice for a mathematician to see such affection for what they do. So the recording of this event will be available on the festival YouTube channel, which can be accessed from the Watch Again section of the festival website. Now, if you would like a copy of Rob's book, it will be available from our partner bookseller. This is Fox Lane Books. For more information on book sales, please see the festival website, or you can head to their webpage of Fox Lane Books, which is foxlanebooks.co.uk.